First of all, let me thank you very much for the invitation. It's really a great pleasure to give this seminar in your seminar series. Great pleasure and a great honor. First of all, I'd like to say that I'm a statistician, and naturally this talk will focus on the statistical aspects of gravitational wave analysis. And as a lot of applied statisticians, I've had the pleasure of working in various different areas and disciplines. And what a lot of applications and disciplines have in common is that you have to analyze time series. Time series means you have observations that have been sequentially observed all the time, and that induces a dependence structure in the data. Applications occur, for instance, in medicine when you're thinking of analyzing the electrical activity of the heart in an ECG, or electrical activity of the brain in an EEG. In medicine, analyzing the temporal trend is important, but also understanding the variability in the data in order to understand normal physiology and how the disease progresses. Another example occurs in ecology, analyzing the Southern Oscillation Index, which is the difference in the air temperatures, in the surface air pressure between Tahiti and Darwin, one of the sort of the key indicators of the so-called El Niño Southern Oscillation Index, which is a recurring, irregularly recurring climate pattern in the Southern Pacific Ocean. And here as well, it's not so much the behavior of the mean over time that's of interest, but the oscillations of the observations around the mean. And that oscillation of these oscillations around the mean, they are also important in when you're analyzing gravitational waves. And I have to admit that the applications in astrophysics, the analysis of gravitational waves, has probably been the most exciting backyards I've had the pleasure to play in, because for thousands of years, mankind has been looking up at the night sky with naked eyes, and since Galileo with telescopes, and we can observe the universe in gamma ray, X-ray, ultraviolet, up to radio waves. But most of the universe is dark and will never be able to be observed in any type of electromagnetic radiation. So the question could be, could we also listen to the universe? But of course, that's nonsense. Sound waves need air to propagate. There won't be any sound in a vacuum, but what does propagate through the universe are gravitational waves, according to the Einstein's prediction from general relativity 100 years ago. And since 2015, we actually know what the sound of two black holes colliding sounds like. And you've probably all heard that. That has this characteristic chirp. And that was observed on the 14th of September 2015. That's when the two LIGO detectors directly measured gravitational waves for the very first time. The signal came from the inspiral of two stellar mass black holes that coalesced to form a single rotating black hole, and signal waveform matching the predictions of Einstein's theory of general relativity. The signal lasted only a fraction of a second, so it was a very short signal. And with this, LIGO's opened a new window to the universe through which we can observe events that would be hidden to electromagnetic telescopes, because gravitational waves can pass through any matter. They're not obstructed by matter like electromagnetic waves. And since then, since this very first black hole merger, LIGO has observed 90 further black holes and is expected to observe many more in the future observing runs. What I'd like to do in this talk today is give you just a brief introduction into the historical events that led to this breakthrough discovery, for which the founders of LIGO, Kip Thorne, Barry Barish, and Rainer Weiss were awarded the Nobel Prize in Physics in 2015. And then I'll focus on parameter estimation, statistical techniques for estimating the parameters of these gravitational waves, and in particular, I think what is the most important aspect as well, the estimation quantification of the uncertainty or the spectral density estimation. And then I'll finish with an outlook to the LISA space mission. So first of all, what are gravitational waves? Gravity in general relativity is not a force, but a deformation of the four-dimensional manifold of space-time. Massive objects, such as our sun and the Earth, have gravity and they'll deform space-time. The more massive the objects, the more space-time will curve, and gravitational waves are ripples in this fabric of space-time caused by accelerated massive objects. And general relativity, just in a nutshell, according to John Wheeler, is matter tells space-time how to curve, and space-time tells matter how to move. So gravitational waves propagate at the speed of light, and they squeeze and stretch any matter that they pass through in a very characteristic way that gives us information about the emitting source. And they have their effect is orthogonal to the distance or to the direction of propagation, and they come in a plus and a cross polarization. And the effect is illustrated here on a ring of test particles. Passing gravitational wave will simultaneously stretch the distance on the horizontal axis while squeezing the distance between two test masses on the vertical axis. It's the plus polarization. Cross polarization is exactly the same effect, but rotated by 45 degrees. So what that means for measuring gravitational waves is that we simply need to be able to measure a distance or the change in the relative spacings between two test masses, the so-called dimensionless strain, delta L over L. But it turns out that space-time is quite rigid, so the amplitude of these gravitational waves that are emitted by cataclysmic events in the universe, such as black hole mergers, once they reach Earth, they are in the order of 10 to the power minus 21, so 1,000 times smaller than the diameter of a proton. And that basically explains why it's been so difficult to measure gravitational waves. I'll skip this one, but go straight to how gravitational waves are measured. They're measured by Michelson interferometry, and the principle is very simple. Laser light is split into two beams, and they're sent down two perpendicular vacuum tubes, at the end of which are test masses suspended on a pendulum. And these test masses are mirror coated, so the laser light is reflected and travels back in these tubes, and these arms of the tubes have exactly the same length LIGO and Virgo have 4 kilometer long arm lengths. So as laser light travels at the same speed of light in both arms, and the arms have exactly the same length, upon recombination, there will be a destructive interference pattern and no laser light will be detected at the photodetector. But if a gravitational wave passes, it will squeeze one arm and it will stretch the other one. So laser light will travel back faster in one arm than the other, and the corresponding interference pattern is measured. So that's how gravitational waves are measured. And prototypes of these interferometers were built already in the 1970s by Renate Meyer at MIT, by Heinz Billing at the Max Planck Institute in Garching in Germany, and by Ron Drever in Glasgow. Ron Drever later on moved to Caltech to join Kip Thorne in the analysis of gravitational waves. And it is expected that he would have been one of the Nobel Prize recipients if he hadn't died before the Nobel Prize was awarded in 1997. So in the 1980s, Caltech and MIT scientists joined forces and conducted a feasibility study to build two detectors, one at Livingston, Louisiana, and the other one in Washington, Hanford, Washington, with 4 kilometer long arm lengths. And they submitted an application for funding to the National Science Foundation that was carefully evaluated, and they obtained funding in 1992. Barry Barish became the new LIGO lab director in 1994, and he made things really happen, and construction started. In 1997, the LIGO Scientific Collaboration was formed under the directorship of Renate Meyer. That scientific collaboration was tasked with the scientific aspects of the project, not the construction. And then it took another 5 years until 2002 for LIGO to become operational. And apart from those two LIGO detectors at Hanford and Livingston, there's also a shorter arm length detector, Geo 600 in Hanover, Germany. and a LIGO detector in Italy, close to Pisa, with 3-kilometer-long arm lengths. Cryogenic underground detector has just been built in Japan, Kagra, and Kagra is going to join LIGO and Virgo in the next observation runs, just supposed to start at the end of this year. And then there's another one planned in India as well. So it's quite important to have a network of ground-based detectors to increase the detection confidence. If you see the same signal at both detectors or at several detectors, can be a lot more confident that that is a gravitational wave signal and not just some truck driving past one. But it's also very important to have several detectors to be able to accurately locate the source of the signal in the sky. So from 2002 till 2010, while LIGO was operating, no gravitational wave whatsoever was observed. And then the NSF decided to upgrade LIGO to increase the sensitivity. That's been done by installing better optics parameters, mirror suspensions, mirror coatings, insulation systems, and control systems. That whole upgrade took another 5 years until 2015, and that increased sensitivity of LIGO by about a factor of 10. And then shortly afterwards, when LIGO was switched on, the corks popped with the detection of the black hole merger in September 2015. The signal was detected at both detectors using the LIGO detection pipeline, which is based on matched template searches. And if you take the delay in the signal arrival time into account and overlay both signals, they basically match perfectly, and they match the predictions of gravitational wave signal that would have been emitted by a compact binary coalescence from the theory of general relativity. So that is the detection of the signal, but after the detection, the physicists also want to say something about the emitting source. Can we characterize what triggered this gravitational wave, and can we say more about that, the source of the gravitational wave? If it's two black holes, how massive they were, at what distance, and so on. That brings us to waveform estimation, estimating the parameters of the gravitational waveform parameters. And for that, we need a statistical model, and the usual model we assume is that the data or observations can be composed into a signal, gravitational wave signal, and residual noise. And that gravitational wave signal is characterized by a number of parameters that are entered in a parameter vector theta. They are the masses of the black holes, the distance, the inclination angles, and so on, and the residual noise. So it has these two components, signal and residual noise. So let's look at those two components one after the other. There are various gravitational wave signal waveforms that are within the LIGO frequency band. They can be categorized into 4 categories: continuous, burst, stochastic, and in spiral gravitational waves. And sort of the characteristic waveforms are illustrated here. What are the continuous waveforms? They are emitted by systems which have a relatively constant frequency. For instance, black holes or neutron stars, binary systems that orbit at a constant frequency, sort of at the in spiral phase, far from merger. But they can also be emitted by pulsars, rapidly rotating neutron stars. Their gravitational waves is at twice the rotational frequency, and the waveform is continuous. It's sinusoidal but Doppler modulated. That's one continuous source. So far, LIGO has not detected any gravitational waves from pulsars, mainly because the gravitational wave signal is relatively weak. Then there are these short burst signals, transient signals that originate from the generation of neutron stars or black holes in a supernova event. These single events are relatively short, consisting of just one or a few orbits, and they are generated in supernova events. The life of massive stars usually ends with the collapse of the iron core under its own gravity. collapse, the so-called core collapse supernova events, it's followed by a supernova explosion. And the supernova event will emit gravitational waves, which, if they happen within 5 to 10 kiloparsecs of Earth, will be within the LIGO frequency band. But these events are relatively rare and estimated that there will be only sort of 3 per century. And so far, LIGO has not detected any supernova events. Supernovae are also visible by electromagnetic telescopes, but physicists are extremely interested in observing these through gravitational waves, because that will give them a lot more information about the physical processes at core collapse. Then there's the stochastic gravitational wave background. So what's that? That is basically the combination or the superposition of all signals, individual signals that cannot be individually resolved. These could come from, could have astrophysical origin, or these binary spirals, the supernovae, the continuous signals that all combine to form the gravitational wave background, or sort of a hum in the background. Or it could have cosmological origin, because the physical processes at the very early universe, such as cosmic strings or phase transitions, will have emitted gravitational waves, which would be visible as a stochastic background today. And it's sort of analogous to the electromagnetic similar to the cosmic microwave background, but with electromagnetic waves we can only see as far back as 300,000 years after the Big Bang. With gravitational waves we can explore the very early universe. So so far also LIGO has not detected any gravitational waves of the stochastic gravitational wave background. What LIGO has detected are 90 compact binary coalescences so far in the first 3 observing runs. And these waveforms are very well understood as these compact objects. It could be 2 neutron stars or 2 black holes, or a neutron star and a black hole. As these orbit around each other, they lose energy due to the emission of gravitational waves. So their orbital distance decreases, their orbital frequency increases. So they are orbiting faster and faster around each other until they merge, and if it's 2 black holes, they'll form a single rotating black hole, which then emits gravitational waves at a much damped down amplitude and a more constant frequency. And that is this characteristic chirp signal, the in-spiral phase reasonably constant, and then increasing in amplitude and frequency until the merger, followed by this ring down phase. And this signal gives a lot of information about the masses and the distance to the object. So let's look at that gravitational wave strength signal in a bit more detail. It is a combination of the plus and the cross polarization, where these antenna beam patterns depend on the sky location in terms of right ascension and declination angle and the polarization angle psi. They're not really time dependent, because these signals are short, fraction of a second, so the rotation of the Earth does not really come into any effect here for these short burst signals. And these plus and cross polarization, waveform polarizations, they can be characterized by time dependent amplitude and phases, but these don't have an analytic exact waveform solution. They can only be approximated by solving the Einstein equations perturbatively using the post-Newtonian order of various post-Newtonian approximations of various different orders. And these post-Newtonian orders approximation waveforms, they are reasonably accurate for the in-spiral phase, but if it gets closer to the merger, they have to be combined with numerical relativity solutions of the Einstein equations. So these waveforms are basically not available in an analytic form, but they can be generated using numerical relativity simulations. And these waveforms can be characterized by 15 parameters. We need 9 parameters to describe a circular binary with no spin. And these parameters are the masses of the 2 black holes, the distance to the source, the sky location parameters, the inclination angle, polarization angle, the time of coalescence, as well as the orbital phase. And we need further 6 parameters to include the spins, the magnitudes, and 2 angles for each object. So that it's basically the gravitational wave signal of compact binary coalescence. What about the residuals? Here is 1 second of real LIGO noise sampled at 16 kilohertz from the 6th science run. And from that, we can't really see terribly much about the features of that noise. But if we sort of zoom in a bit more, we see that it is definitely not independent, not white noise, but at least it looks stationary. And stationary noise is usually no problem for any point estimates of the waveform parameters. But what it affects is the uncertainty quantification, the standard errors around those parameter estimates. And that's quantification of uncertainty is one of the most important aspects of statistical analysis. So I'd like to look at that residual noise, or modeling that residual noise in a bit more detail. So if we assume that the residual noise, LIGO noise, is mean zero stationary, then its dependent structure is characterized by its autocovariance function, which is a positive semi-definite function that is the correlation between, or the covariance between, 2 observations that are a lag k apart. So it's not time dependent, it only depends on the distance between the observations. And that can alternatively be characterized by the spectral density, which is the Fourier transform of the autocovariance function. And that spectral density basically splits up the whole variance into the power, or the whole power into its frequency components. So that uniquely characterizes the second order dependent structure, which we are interested in. So the assumptions we're making on the LIGO instrumental noise is that it is a Gaussian stationary noise with a known power spectral density. That basically means we are dealing with a multivariate Gaussian observation, and in order to evaluate that multivariate Gaussian likelihood, we would need to invert a high-dimensional covariance matrix, which depends on that power spectral density. And inverting such a high-dimensional matrix is, if not impossible, but it is at least very mathematically unstable. So to avoid that, one usually uses a likelihood approximation in the frequency domain. And that's based on the fact that if one Fourier transforms the data into the frequency domain, the Fourier coefficients have an asymptotic normal distribution again, but they are asymptotically independent. So that the Fourier transform diagonalizes the covariance structure, diagonalizes the covariance matrix. So to evaluate that likelihood, approximate likelihood in the frequency domain, we no longer have to invert a high dimensional matrix. We just have to divide by the spectral density. So much easier, and that's why we usually work with this likelihood in the frequency domain. If we want to use a Bayesian approach, we would need to put priors on our waveform parameters, and we usually use non-informative priors, so uniform on the masses and so on. And then we would calculate the posterior distribution, and we would use numerical methods to sample from that posterior distribution. 2 methods that are implemented in the LIGO inference library are a Markov-Chain Monte Carlo methods, the MCMC, that's based on parallel tempering, and nested sampling. So if both methods give the same parameter estimates, then LIGO can be very confident that these are correct. For instance, the masses of the 2 black holes of the very first observation were estimated to be roughly 30 solar masses at a distance of 410 megaparsecs. With 2 detectors, LIGO could also give a rough estimate of the source location in the sky, and we can also reconstruct the time signal, and that matches the observations quite well. Now let's have another look at the assumptions on the residual noise. We've assumed that the power spectral density is known, but of course we do not know the power spectral density, but we can estimate it. And what's usually done is power spectral density is estimated from separate stretches of the data, separate stretches that do not contain the signal, but that are in a neighborhood of the signal. And then one calculates the parallelogram for each stretch and averages over the periodograms to obtain a consistent estimate of this power spectral density. And then for the purpose of parameter estimation, that spectral density estimate is assumed to be fixed and known and entered as a fixed constant in the likelihood function. But that totally ignores the remaining uncertainty about the instrumental noise, about the spectral density of the noise in this likelihood. And that has consequences, not so much for the point estimates of the parameters, but for their uncertainties, for their standard errors. And that has been realized over, especially over the last, say, 33 years. Several papers have appeared in the literature that pointed out that the negative aspects of assuming that the spectral density is known and ignoring the uncertainty about the spectral density estimate, and pointing out that it would be better to simultaneously estimate the noise spectral density and the gravitational wave parameter from the same stretch of data. And for that, we basically need, again, the Whittle likelihood approximation and the frequency domain, but we need to treat theta as an unknown parameter, but also the spectral density as an unknown parameter to be estimated. Here is 1 second of LIGO noise downsampled to 4 kilohertz in the frequency domain. That's the periodogram on the log scale. And this is very characteristic. What we see is a lot of high power narrowband spectral lines. And these lines are important to be estimated accurately, because after each observation run, the engineers are trying to, or the whole instrument is engineered, and these spectral lines are try to be kept as close to as narrow as possible. These spectral lines are can often be traced back to known instrumental sources such as 60 Hertz power lines or the violin modes from the mirror suspensions. And it is important to characterize these and trace them back in order not to confuse them with any actual burst signal in the data. So ideally, what we want to develop is a Bayesian approach to spectral density estimation that is non-parametric, so it doesn't depend on any parametric assumptions, which may or may not be justified, that is flexible enough so that it can pick up these sharp, narrow peaks, that has good statistical properties such as posterior consistency. Consistency basically can be regarded as a measure of robustness, asymptotic robustness. It means that with increasing sample size, the spectral density estimate should concentrate around the true spectral density. That's sort of a reasonable, a minimal characteristic that we would expect our estimate to have. And that is, of course, immediate if we're using parametric method, but if we're using non-parametric method, we need to prove that our estimate is consistent. And it is like robustness. It basically means no matter what our prior assumptions are, if we increase our sample size, we will estimate our estimate will get closer and closer to the true spectral density. And then we want a technique that we can combine with simultaneously estimating the waveform parameters. So that's the problem from a statistical point of view. And that basically brings me to spectral density estimation, to Bayesian non-parametric spectral density estimation. As I said, we're using the Whittle likelihood approximation that goes back to New Zealand-born statistician Peter Whittle. And various non-parametric priors for the spectral density have been suggested in the literature. Only one of those actually proves posterior consistency, and that is Schauder's contribution, which is based on the Bernstein-Dirichlet process prior. So what's that? It looks quite complicated, but it's actually not. You probably all know that you can approximate any continuous function by a mixture of or combination of Bernstein polynomials. By increasing the order of the Bernstein polynomials, you can get as close to your function as possible. And that's basically what the Bernstein-Dirichlet process prior is based on, a representation in terms of mixture of Bernstein polynomials. So I'll show you a picture that makes that a bit more clear. Here we've got Bernstein polynomials of order 10. So 10 basis functions, which all attain their peaks in different subintervals of the interval 0, 1. So that's standardized to the interval 0, 1 instead of 2 pi or whatnot. If you imagine that each of these basis polynomials has a weight attached to it, and we take the weighted average of those basis functions, then we obtain a mixture representation. So any spectral density can be represented in terms of such a mixture. So if we go back, what we can assume is that these weights are all positive and sum to 1, that they are generated by a distribution function g on the interval j minus 1 over k to j over k. That's where the j basis polynomial attains its maximum. But we don't want a parametric method. We want a very flexible method. So we put a non-parametric prior on g on this distribution. And such a non-parametric prior is the Dirichlet process. So we put a Dirichlet process on g, and we also put a prior on the polynomial degree. So we don't fix that, we leave it flexible. Put a prior on k, and k is a smoothing parameter. The smaller k, the smoother the function, the larger k, the more wiggly is the resulting function. So by putting a prior on k and estimating k, we get an automatic data-driven degree of the smoothness of the spectral density. And how does that work in practice? We are sampling a realization of the Dirichlet process, and the Dirichlet process is a discrete distribution on the interval 0, 1. And here I've color-coded them. If we sum up the realizations in one subinterval, or all those with the same color, that gives us the weight that corresponds to that Bernstein polynomial. And then we average over those Bernstein polynomials, and we get that mixture representation. So not terribly complicated. So if we use that Bernstein-Dirichlet process prior, combine it with a Whittle likelihood, calculate the posterior distribution, sample from it, and estimate, for instance, the posterior mean, we get this spectral density estimate. And it's overlaid by the periodogram. And just one example, the example I've used here with the Southern Oscillation Index. And this is very characteristic. What we see is that it oversmoothes. It does not pick up this sharp peak. And that is because Bernstein polynomials are good at approximating smooth functions, but not so good at approximating peaks. So that's not really very useful for our LIGO applications. So an alternative is to move from Bernstein polynomials to B-splines. And that's also the idea of Bayes wave, which is heavily used in gravitational wave data analysis for LIGO and Virgo. Bayes wave uses a mixture of B-splines, but the way, instead of putting a Dirichlet process prior on the weights, it uses basically a fixed dimension and jumps through the dimensions using a reversible jump type algorithm, which is notoriously difficult to tune. So that's why I think the Dirichlet process prior has some advantage. But here I want to suggest to stay with the Bernstein polynomials, but change the likelihood or modify the likelihood by taking advantage of a parametric auxiliary model. So the idea is we can improve our technique or our method by taking advantage of a parametric working model. And a class of models that can approximate a lot of stationary time series are the Gaussian autoregressive model of order P, and they have a closed form spectral density. It's the form of the spectral density of a Gaussian autoregressive model of order P. So the idea is to start with such a AR model in the time domain, Fourier transform, and in the frequency domain, correct for some potential misspecification by correcting it with a diagonal matrix or multiplying by a diagonal matrix, which contains the ratio of the true spectral density to that of the auxiliary AR spectral density. And then back transform, and we call the likelihood that's induced by this transformation the generalized Whittle likelihood. The likelihood under that autoregressive working model. Why is it a generalized likelihood? Because if we would start with an AR0 model, an AR0 model is just a Gaussian white noise model, independent errors. Then if we start with an AR0 model, do this whole transformation, we get the ordinary Whittle likelihood. So this is a generalization, but you can sort of glimpse why it might be advantageous instead of starting with a white noise model. When you know that you've got dependencies in your residual noise, it's much better to start with an autoregressive model, which can at least approximate part of that dependent structure, and then correct it with non-parametrically. And that's what we're suggesting to do. And we're not putting the Bernstein-Dirichlet process prior on F, but we put it on the correction function, because the idea is if the autoregressive model fits well, this ratio will be much smoother function, and smooth functions can be better approximated by Bernstein polynomials. And then we can prove posterior consistency, and that's illustrated here. What it means is we have simulated data from an autoregressive time series of sample size 128. And this is the true spectral density, that black curve, and the purple curves give posterior credible bands of our generalized Whittle likelihood estimate. And what posterior consistency means is that if we increase the sample size, these posterior credible bands will get narrower and narrower and closer and closer to the true spectral density. That's what posterior consistency means. And you can find the proof, the mathematical proof in the Bayesian analysis paper that appeared in 2019. But I'd just like to show you the application to LIGO. Here we've got, in general, we also want to estimate the parameters of the auxiliary model simultaneously with the spectral density. So we could put priors on both. And we've implemented this in an R package called Beyond Whittle, so it's freely available on CRAN. And we've done a big simulation study, and we found excellent properties of this. If the parametric model, this AR model, is well specified, then using the generalized Whittle likelihood will be almost as efficiently as the parametric model. But if it's misspecified, it will be robust. It will be as robust as a non-parametric model. But in the partially misspecified case, it outperforms both the parametric and the non-parametric technique in terms of mean squared error and coverage probabilities. Before I show you an application to LIGO, I'll show you an application to the Southern Oscillation Index, which I've used before. Here, if we start with a Gaussian white noise working model, we get an estimate that is overly smooth. So that's the ordinary Whittle likelihood. That's too smooth. If we start with an AR5 model, the dashed curve is a fit of an AR5 parametric model. If we use that as an auxiliary model in our generalized Whittle likelihood approximation, then we get this estimate, which can pick up this peak. And this peak actually corresponds to the annual cycle in that Southern Oscillation Index. If we use an AR11 model, here the dashed curve, then we can also pick up the half-yearly and the seasonal peaks due to seasonal variations. If we go to an AR15 model, we pick up this wide band peak at low frequencies, and that can be interpreted as the El Niño effect, that the oscillations between warming and cooling phases, between El Niño and La Niña phases, which occur every 4 or 5 years. And here's an application to LIGO data. The red curve is the estimate obtained by the ordinary Whittle likelihood. Too smooth, again, it doesn't pick up these sharp peaks. If we use or the parametric model, an AR35 model in this case, is the blue dashed curve. And that already gives a reasonable approximation, but it misses some peaks, and it sort of shows peaks where there's nothing visible in the periodogram. But if you use that as a working model, as an auxiliary model for the generalized Whittle likelihood, we get a technique, a spectral density estimate that picks up all these sharp peaks. And here it's overlaid with 95% credible intervals. And as I said, we also want to estimate the spectral density simultaneously with the gravitational waveform parameters. And we can do this in a Gibbs sampling approach, in a block Gibbs sampler. Sort of, we fix the spectral density, the gravitational wave parameters, take the residual and estimate the spectral density based on the residuals. Once we have an estimate of the spectral density, we fix that, and for fixed spectral density, estimate the gravitational wave parameters. And then we keep on doing this in a cycle, which is so-called the blocked Gibbs sampler. And that's been illustrated in a few recent papers. So this spectral density estimation techniques are important for LIGO, but they might be even more important for the future space mission LISA. So why a space mission LISA? Why would you put interferometers up in space? That is because LIGO is operating at a frequency range between 20 Hertz and 2 kilohertz, and at low frequencies, it's very limited by environmental noise components such as anthropogenic noise, microseismic noise from the ocean waves or the clouds, the lunar tidal forces, as well as the global weather systems in the microhertz range. So to eliminate all these environmental noise components, the idea is to put the interferometer up in space. That's the idea of the space mission LISA that's led by the European Space Agency with support from NASA. The launch is expected to be in 2034. Plan is to put 3 spacecrafts in an equilateral triangular formation in an orbit around the sun, trailing the Earth, as sort of depicted here. And instead of 4-kilometer long arm lengths, LISA will have the 3 interferometers will have 2.5 million kilometer long arm lengths. So LISA, in contrast to LIGO, will observe gravitational waves with much longer wavelengths and different types of sources that emit these long wavelength gravitational waves. For instance, the supermassive black hole mergers, or EMRIs, extreme mass ratio inspirals, which is the inspiral of solar mass black hole around a supermassive black hole, or also the gravitational wave signal from the galactic white dwarf binaries. And last not least, the stochastic gravitational wave background as well, much longer wavelengths. And I think I've got a little bit more time. Basically the key features of the stochastic gravitational wave background, whether it comes from an astrophysical or cosmological origin, is lies within the form of the power spectral density. And here I think statistical methods to estimate the power spectral density are quite important. So far we've used parametric spectral density estimation methods based on power law forms of the stochastic gravitational wave background, as illustrated here, just a straight line on the log-log scale. But I would think that non-parametric methods, such as the ones I've outlined before, can be very important for LISA to distinguish between the various different types of stochastic gravitational wave backgrounds. And then we've got a lot of further challenges that LISA provides. LISA is not just LIGO in space, and we can use the same techniques. Again, it has its unique challenges. For instance, the LIGO interferometers were well separated on Earth, and the instrumental noise could be safely assumed to be independent. That's not the case with LISA. The LISA interferometers share their arms, so the noise will be cross-correlated. So we basically have to deal with a multivariate time series. And I probably might have to shorten this because I'm running a little bit out of time. We've basically generalized our Dirichlet process, Bernstein-Dirichlet process prior approach to estimating the spectral density from a univariate to a multivariate time series. And for a multivariate time series, the spectral density is no longer a real valued function, but is a complex matrix valued function, which on top of it is positive definite at each of the Fourier frequencies. So various techniques have been suggested, and they're based on smoothing the Cholesky decompositions to preserve the positive definiteness, but none of these have shown posterior consistency nor an automatic choice of the degree of smoothing. And we've generalized our Bernstein-Dirichlet process prior to a matrix gamma prior. I'll just show you this on a figure and an illustration. Here we've got again our Bernstein polynomial basis. Now, instead of having a real valued process, we have a matrix, complex matrix valued process. The real realizations on the diagonal complex and real parts of the cross spectrum on the off diagonal. So we basically get the two spectra of the bivariate time series on the diagonal, the real and imaginary parts of the cross spectrum on the off diagonal. Using an HPD matrix gamma process, construction is complicated because the usual generalizations of the gamma to a multivariate gamma are not infinitely divisible, and that sort of really needs a complex construction using the Kingman construction of the matrix gamma process. But we've basically implemented this and proved posterior consistency as well. And that's implemented in the Beyond Whittle package as well. It's integrated in this package. So it can handle multivariate time series as well. And here is again that Southern oscillation example. If we apply this, what we see again is that we're using the Whittle likelihood over smoothers. It does not pick up the sharp peaks. And that's why we've combined it with a multivariate generalized Whittle likelihood. And we managed to prove posterior consistency as well. And with the auxiliary vector autoregressive model, we can pick up sharp peaks as well. Further challenges are from the LISA Pathfinder mission, which was flown in 2017. We know that we have need to expect glitches, large outliers in the data, and that's not really consistent with the Gaussian distribution assumption. So one of my PhD students has proved that the approach also holds in the general case of non-Gaussian data under certain regularity conditions. So that's good news, even if you do not have Gaussian observations, even in a non-Gaussian case, you get posterior consistency. And LISA, in contrast to LIGO, will observe not just short duration signals, but will observe long duration signals, long wavelengths over a long period of time. So assuming that the noise is stationary is not a realistic assumption anymore, and we need techniques for locally stationary time series. And we've started to develop these local techniques for a locally stationary time series, such as this one here. It's a simulation of a time-varying autoregressive process. And what we've basically used is some short-time Fourier transform, what we call the moving Fourier coefficients. We can prove that these have similar properties to the global Fourier coefficients. And by generalizing the Bernstein-Dirichlet process from a one-dimensional process to a bivariate process, we can combine this and estimate locally time-varying spectrum, these evolutionary spectra, which change over time as illustrated in these simulated data. And again, these techniques have good statistical properties. So I focused a lot on spectral density estimation, but there are an awful lot of other data challenges that need to be solved before LISA can actually, LISA data can be analyzed. The source confusion problem, because once LISA is up in space, it will basically be bombarded from all sides by signals, and it's important to be able to distinguish and individually resolve these signals. I've already mentioned the separation of the various origins of the stochastic gravitational wave background. We have to deal with data gaps and also the signal modulation, which is induced by the orbital movement of the interferometers around the sun. With this, I'd like to finish and acknowledge a lot of my collaborators from within LIGO and the LISA collaboration, in past and present PhD students, without whose contributions this work would not have been possible. I'd like to acknowledge funding from the Royal Society of New Zealand and the Deutsche Forschungsgemeinschaft. And I'd like to point out our New Zealand Gravity Group in New Zealand, which is a working group of New Zealand statisticians as well as physicists and mathematicians that are all in some way interested in the analysis of gravitational waves and in making contributions to the analysis of LISA. And we've joined the International LISA Consortium Working Group, and we would value any type of collaboration. So thank you very much for your interest and your attention. And I hope I didn't go too much over time. Sorry again for the late start.
Thanks a lot, Dr. Meyer, for this very informative talk. Do we have questions?
May I ask one question, please?
Yes, of course.
Very interesting that you're working on almost all gravitational wave detection researches. I wonder have you ever worked with a pulsar timing array, and if so, what could be the reason of non-detectability of gravitational waves by PTAs for a decade? Is it that something we lack with the to improve the signals or data processing skills, or is it with the the sensitivity of the timing array by itself? So
that's an excellent question, but that is basically out of my sort of expertise. I've never worked with pulsar timing arrays, but in our New Zealand Gravity Group, we've got Willem van Straten, who has been working, who's a member of the pulsar timing collaboration and working closely with Osgrave. So he would be probably one of the experts, but I would say that I can't really answer that question. I haven't worked on pulsar timing at all. Sorry.
Okay. Thank you very much.
I
just thought because you're working almost on every gravitational wave detector, so maybe.
Not on the pulsar timing, but I'd be very interested because the potential is there to detect the stochastic gravitational wave background with pulsar timing. So I'm in the future, I'm extremely interested to get involved, and there might be some potential to work with Osgrave and Willem van Straten on that.
Thank you.
Do we have any other questions? Okay, so I think we're done.
May I ask a question?
Yes, of course.
Yes.
Thank you for the great talk. It was really interesting. What I would like to ask is, since the LISA will be detecting a lot of signals at the time, you also talk about the confusion noise and all that. How would we like if LISA is detecting one signal and then we know that there is another signal incoming, how would we remove, or how will we differentiate the signals from one or the other? Since LIGO is detecting a very short signals that can be differentiated, that one signal is coming, then it has finished, and then the other signal is coming. But in case of LISA, there are long signals as well. If there is a long signal in like recording, or I don't know how to say it, that LISA is detecting one signal, and then we know that from other telescopes that another event of the same like precedence is occurring, how would we differentiate those signals in LISA?
That is an excellent question, and that is what's usually referred to as the source confusion problem. So various different signals are coming in at the same time. They're overlapping not just in time, but quite often also in frequency. So some of these will be able to be individually resolved if they can be separated in their frequency component. And then the one strategy is to subtract one signal that has been resolved from the data and then sort of sequentially resolve the other signals. But that signal subtraction also could introduce some bias in the whole estimation process. So I think it is much better to use sort of a Gibbs sampling approach where you are trying to estimate all the signals at the same time rather than subtracting them off. But there will be signals, you're totally right, that will not be able to be individually resolved. And these will make up that part of that stochastic gravitational wave background of the astrophysical component. So we distinguish between various different stochastic gravitational wave background. The most prominent one will be from our galaxy, from the nearby white dwarf binaries that will form sort of a foreground. And that there are millions of these white dwarf binaries, and it's impossible. It's sort of estimated that one can individually resolve sort of 10,000 of those, but the rest will not be able to be individually resolved. But we can estimate that because this will be a non-isotropic signal because of the orbital motion of the interferometers around the sun at various times in the year. They will be closer to the center of the galaxy, and using that modulation, we will be able to subtract that, hopefully that astrophysical foreground, and then sort of within a sort of Gibbs sampling approach, simultaneously estimate and separate out the other signals. I think this is a huge challenge, and I don't want to say that I don't think anybody has the answer to that, but people are working on that, and I think sort of a simultaneous approach based on Gibbs sampling with various other methods might be the most promising approach here.
Thank you very much. Another thing that I want to ask is that whenever like I've read about the detection of gravitational wave, they say that the signal has matched a template that was like sort of there generated by the general relativity. So is it that every template, not every template, or some potential templates have already been modeled and they are like present in some sort of data set or like this that are matched with the signals? Is that something that happens?
It's exactly what happens. The physicists have created a template bank of templates or of signals based on sort of parameters which are allocated basically on a grid for the masses, for the most important parameters. And then one basically goes sequentially through those template bank and tries to match the signal in the template bank with the observed signal in terms of so-called matched filtering. Once one finds a template in that template bank that matches the gravitational wave signal, and that's the same at both detectors or 3 or 4 detectors, then one can claim a detection. And from then on, the parameter estimation pipeline is used to more accurately estimate the parameter values.
Thank you very much.
Do we have other questions? Okay, I'll ask a quick question. At the beginning, you showed a few projects of gravitational wave detectors. You had the slide where you showed a few projects. And so is there a way to combine the data from different projects and analyze the data together? Or
that is exactly, if we have two LIGO detectors, what is usually done for parameter estimation is they are assumed to be independent. So they're basically combined. The joint likelihood is the product of the individual likelihoods.
okay.
And so that increases the uncertainty about the parameter estimates if you can have observations from two detectors. You just need to be a bit careful. You need to take that difference in the signal arrival time into account, but that can be easily done.
Okay.
So that's basically, you use the product of the likelihoods because you assume that the instrumental noise in one detector is independent of the instrumental noise at another detector. There are sort of scenarios where you can, or where people, or what the physicists have also looked at, is the so-called Schumann resonances. I'm not quite sure what causes these Schumann resonances, but it is feasible that there are correlations between there are features in the environmental noise that could affect both detectors at the same time. But these are usually so weak that they don't play any role for gravitational wave detection.
So potentially, when we have LISA, when LISA is launched, you'd be able to combine the data from LISA and some Earth-based detector as well?
Potentially, yes, but you could, for instance, use LISA to observe a black hole merger far from coalescence in the in-spiral phase before it gets into the LIGO frequency band. And in LIGO, you just see the last few milliseconds before the merger. Yes, potentially yes, but LISA is really sensitive to different types of sources than LIGO. But the in-spiral phase of compact objects, binary compact objects, that would be visible within the LISA frequency band, and then afterwards and close to merger in LIGO.
Yeah, a potential sort of multi-wavelength sort of analysis, the equivalent of what we do in electromagnetic observations.
And I mean, the gravitational wave observation will be very important for an electromagnetic follow-up if it's a neutron star merger, as we've seen in 2017. Yeah.
Okay, so that's great. That's great. No more questions? Okay, well, thank you very much for this great talk. And
thank you very much for having me. That's great.
Okay.
All right.
I'll end the meeting now. Okay.